The injection system, as it is presented here, is the result of a cooperation project between Statkraft, Flow Design Bureau and Statkraft. The goal of the project was to develop a system capable of reducing damaging mechanisms during part load of the Francis turbine. Ultimately, this would enable the power plant to utilize a larger spectrum of flows. The idea was first developed by Dr. Morten Kjeldsen by requests of Statkraft. One of their power plants is subject to minimum flow requirements, a flow that would damage the turbine under normal circumstances. As the water is distributed to the runner, the energy contained in the water is transformed by the turbine. After passing through the runner, the water should drop down the draft tube, depleted of all potential and kinetic energy. This is, however, only in theory. At the design load, the efficiency is at its peak. That means that the turbine will extract almost all the energy from the water. This results in a smooth flow through the draft tube. However, as the load shifts away from the best efficiency point, more residual energy will be left in the water. This residual energy will result in a spin of the water in the draft tube. At part load, where the efficiency has dropped heavily and where the flow still is substantial, the rotation of the water will be such that heavy backflows and pressure pulsations can occur. These pressure pulsations can in time cause fatigue fractures to the runner. This chart, provided by the turbine runner supply Alstom, shows clearly the effects of part load on the potential lifespan of a runner. 50,000 times longer life expectancy for a runner only working at best point efficiency instead of at part load. The idea of the injection system is, as the name implies, to inject water in the opposite direction of the spin. This reduces the rotational energy and improves the flow through the draft tube. Ultimately, this should hinder the birth of heavy part load pressure pulsations. The system was tested out on 2 of Statkraft's power plants with good results. Statkraft's involvement started in 2009, as a cooperation project was launched with Statkraft and Flow Design Bureau. The goal was to develop 2 auxiliary systems. The first one, a protective system. The injected water is highly pressurized, and an eventual leakage or waterway failure has to be detected and immediately countered. Secondly, it is imperative that the injection of the water is regulated. This is done according to the flow, or in fact by the guide vane position. Also, detected pressure pulsations have to trigger the system. One should be able to consider the system as a standalone product, which is why the auxiliary systems were imperative to develop. To be able to control the system, a human-machine interface was created. It can be used to manually override command lines and surveil the state of the different components. Just as for Statkraft's power plants, the system efficiently dampened the pressure pulsations experienced at Svorka Power Plant at part load. Further testing of the guidance and protection auxiliary systems were also successful, and the full system is now operational at Svorka Power Plant. A small portion of the water that would be submitted to the turbine is used by the injection system. It could be considered as a direct loss of the turbine efficiency. However, a thermodynamic field efficiency test showed that the improved draft tube conditions led to an increased efficiency of the turbine as a whole, making up for most of the water loss through the injection system. Statkraft completely removed the load restrictions from one of their prototype power plants in 2014 and has experienced no complications since then. Statkraft's next implementation of the system will be in one of our power plants, where part load not only damages the runner, but also had a heavy impact on the draft tube. The concept of water injection should in theory also apply to high loads, where cavitation often can occur. The spin in the water has at this point changed direction, so the nozzles would have to point in the opposite direction. But the effects should remain similar, slowing the rotational speed of the water and thereby increasing the pressure in the draft tube should provide a countermeasure for cavitation on the runner blades. Svorka Power Plant is now equipped with a cavitation detection system and plexiglass windows to provide visual access of the runner outlet. Svorka is a perfect candidate for testing the hypothesis. Statkraft, together with Flow Design Bureau, has now initiated a new research and development project with two goals: quantifying the effects of the system on material stresses at part load, and testing the effects with reversed nozzle positions on cavitation at high loads.